Okay, this is the start of a couple videos on regression lines. Can't fit it all into one video, else it'd be way too long and you guys would just get bored. So we're going to do a couple different videos, probably 3 in total. So this is part 1 of regression lines. First off, a regression line summarizes the relationship between two variables under a few conditions. We talked about scatter plots, which show us a visual picture of the relationship between two variables, but a regression line actually summarizes that relationship for us. Now, there's a couple conditions. The first is that we must have quantitative variables. Both variables must be quantitative, not just one or the other, but both variables must be quantitative. So that's the first condition, that we have quantitative variables. Quantitative variables. Okay, the second condition is that one variable must help explain or predict the other. One variable must help explain or predict the other. So sometimes this involves thinking. You have to think about which variable is doing the explaining. That's the explanatory, or the X variable, and which variable is being predicted. That's the response variable. It's responding to the explanatory variable. So make sure you clearly think about that. Who is who does matter for regression line. Doesn't matter for correlation, we talked about in the last video, but it does matter for regression line. Data must be somewhat linear. Your scatter plot, your data must be somewhat linear. Now I'm going to put that somewhat in quotes because it's kind of vague. You just have to be able to say, well, I guess it's kind of going in a straight line. It's never going to be perfect, especially if your correlation is low, but it needs to be somewhat linear. Okay, you can't see a giant curve in the pattern. That would be bad, obviously. And then obviously regression line is used to predict a response, that's the Y, remember, from an explanatory X. Remember, we're always trying to predict a Y. That's the response from a given X. Okay? So regression line can be used if you meet these 4 qualifications, conditions. Quantitative variable. One variable must be the explanatory. One must be the predictor. Data must be somewhat linear, and it's used to predict a response Y from an explanatory X. All right, let's take a look at one right here. You guys have probably called a regression line called the line of best fit. Well, we're moving up. We're now in an AP college level class. It's called a regression line. No longer are we going to call it a line of best fit. Okay, but it's kind of the same thing, I'll admit that. So here we looked at 16 Ford F-150s. We looked at 16 used Ford F-150s, and we looked at how many miles they had on them and what the price was of them, how much they were being sold for. And each point represents one Ford F-150, and we looked at how many miles that car had and what its price was. And we noticed definitely a negative linear pattern, and we noticed that as the more miles that are on the cars, the lower the price tends to be. So we first have a line that goes through our data. This is what's known as a regression line. It's a line that summarizes what's happening. It's showing a summary of the fact that it's negative, the fact that as the miles get higher, the price gets lower. That's why we call it a summarization line, a regression line. Now, we also see in the picture that we don't fit the data perfectly. Some points are closer, some points are further away, and that's okay. It's just a general summarizing line here. And this line, this blue line, is used to predict miles, or to predict price based on miles driven. Remember, we're always trying to predict the Y. So the Y becomes what we're predicting. We're predicting a response with a given number of miles. So that's a picture of a scatter plot with a regression line drawn through it. Now, what is the equation for an regression line? Well, you guys may remember back in algebra that the equation of a line is y equals mx plus b, where we have slope m and b the y-intercept. Now, that is a straight line, but that's an algebraic way of looking at it. The statistical way of looking at it is y hat equals a plus bx. Now, I might be saying, y hat? What are you saying? Well, this little hat we put on y, this little, it's not a hat. I guess it doesn't look like a hat. You can make it look like a hat. But this little mark here, that is known as y hat. It's actually pronounced y hat. Okay. Now, y hat is the predicted y value. Why don't we use y? Why don't we put a hat on it? Well, it's because it's not actual y. It's just a model. So the little hat there is just signifying to the reader that this is not an actual value. It's a predicted value. Remember, y is the price of the car. So it's not what the car is actually sold for. It's just what our model predicts it to sell for. So the distinguishing between a y and a y hat is really, really important. This first number here is the y-intercept. It is what happens, what do we predict y to be when x is 0? So the y-intercept is what do we predict the y to be when x is 0. So in our case, it would be if we have a car with 0 miles on it, what do we predict the price to be? B, the number next to the x, is the slope. We don't use m in this class. Please keep that in mind. The slope tells us how much y changes when x increases by 1 unit. So it's what the y changes per x. So we'll keep that in mind. We'll talk more about that as the video goes on. But the slope tells us how much the y predicted value changes when we increase the x by 1 unit. We'll talk more about that in a second. Finally, x is actually the given explanatory variable. So in this case, I would give you a number of miles, and you could use the equation to predict how much that car would cost. So let's actually go back to that data, back to our 16 Ford F-150s. So what we're going to do here is I'm giving you the line of regression. The equation y hat equals 38,257 minus 0.1629x. So when we have an equation in front of us, we need to be able to identify, interpret, and predict. So we're going to go through those three things right now. First off, oftentimes we like to not use a generic y and x. We like to actually use words from the problem to make it in context. In context means makes it actually pertain to the problem. So y is the price. So I'm actually going to put price here, but I'm going to put a little hat on it one more time. So the predicted price. This is not an actual price. This is a predicted price. The predicted price of a car is 38,257 minus 0.1629 times the number of miles that car drives. So if you tell me, hey, that car has 84,000 miles on it, I could plug it in to my equation and get a predicted price. Not the actual price, because it's just a model. It's just predicting. So the first thing we have to be able to is identify what is the slope and what is the y-intercept. So I came over here, and it's pretty easy to understand who the y-intercept is and who the slope is. So A is obviously the 38. I'm going to come back here. Sorry if you're making you dizzy here. A is the 38,257. That's my A. And then I have plus b times x. Well, obviously b is negative in this case, so my slope is negative 0.1629. So I came over here. Now that we identified, and that's pretty easy to do, you just got to look at it. Now we need to be able to interpret. Okay, so first off, this a is a predicted y when x is 0. This is a predicted cost when x is 0 miles. So now notice I'm using units here. I'm actually speaking in context of the problem. So this tells me that if a car, I should say F-150 there, if a Ford F-150 has 0 miles, then it is predicted, and you need to always use that word predicted. Never say it will cost, because you don't know that. This is just a model. It is predicted to cost $38,257. Don't forget my dollar sign there. Now, notice I have units. Notice I use the word predicted. And notice that I'm speaking in terms of this is a possibility, right? This is just a model. This isn't guaranteed to happen. Sometimes you will end up with y-intercepts that make no sense. In this case, it could make sense for a car to have 0 miles, brand new car, costing around $38,257. Not completely out of the question, but still just a model. All right, now the slope. The slope, remember, is how much the predicted y changes per 1 unit of x. So here's how I like to make sure interpreting slope becomes easy. Make it a fraction. Put it over top of 1. Right? You can make anything a fraction by putting it over top of 1. And that 1 reminds me that's 1 unit of x, which is us, it would be 1 mile. Okay, remember that the per 1 unit, so slope is how much your y changes per 1 unit of the x. So if I make it a fraction, it reminds me of the per 1 unit. Now the top value here is my y value, which is measured in dollars. So this tells me that for every 1 mile that my car travels, my Ford F-150 travels, I am predicted to have a decrease of about 16 cents. If that makes sense rounding. So let me write that down. For every 1 mile increased, the predicted, and again, I can't emphasize how important that word predicted is. You forget it's going to cost you points. The predicted cost will decrease by 16 cents. So, couple comments here. First, gotta have that word predicted. Please don't forget it. Notice that slope is something that is ongoing. So if I go another mile, another 16 cents goes down. Another mile, another 16 cents goes down. Another mile, another 16 cents goes down. So that's why I like to have that phrase for every in the beginning. Makes it sound like it's ongoing, which is true for a linear regression line. Notice that the x is always increasing. You're always looking at a graph from left to right, so the x is always increasing. The negative on the slope does tell me that my predicted cost is going down 16 cents. Now, it kind of sounds dumb for 1 mile to go 16 cents. So you are allowed to multiply. I can multiply the top and bottom by 10. And as long as I multiply the top and bottom by 10, now I could say for every 10 miles increase, the predicted cost goes down by $16, right? So I multiply by 10, that becomes 10 miles on the bottom, and 16, I take that back. Actually, that would go to $1.63. If I multiplied by 100, that would be 100 miles goes down $16. So hopefully you understand that. As long as you multiply the top and bottom by the same, you are allowed to multiply your slope out. So hopefully that makes sense in terms of interpreting. We're going to get a lot of practice with that, but I went over the key aspects of that. Okay, now, predicting could be a question, right? If I'm going to ask you to predict, I'm going to ask you a question. I could say, predict price of car, truck, I should say F-150, with 84,000 miles. Okay, so what I'm going to do is I'm going to come back over to my equation, and I'm literally just going to plug 84,000 miles in. So on my calculator, I'm going to type in 38257 minus 0.1629 times 84,000, and I get $24,573. Now again, here's 84,000. The line, if I put a dot there, should be right at about 24. Again, it's actually almost right where that arrow's at, right below $25,000. So the predicted cost, and again, I'm going to come back over here so I can show my work. When I plugged it in, would be $24,000, $573.40. So dollar sign there, don't ever forget units, $24,573.40. So all you got to do is plug it in. Now, this equation, this is important right now, flashing lights. This equation was developed, it was created for one reason only, to predict costs with a given miles. It does not work the other way around. I cannot give you an actual price and work backwards to get a predicted miles. Not possible. Algebraically, I understand you can plug in for y and back solve for x, but statistically, it's not possible. This equation was built for one thing only: take miles and predict a cost. It cannot be done backwards. Please note that. That's an important thing. Could be an AP question. All right, now let's talk about something called residuals real quick. So we're going to go back to our scatter plot with our linear regression line on it, and let's talk about a residual. Now, every point has its own residual. So every point has a residual. Okay? Now, a residual, I'm going to talk about the definition of it first, and then we'll actually show it on the graph. A residual value, to figure out a residual value, it's how far away your actual value is from your predicted value. So it's y minus y hat. It's the actual y minus the predicted predicted y. And again, this is why the difference between y and y hat is really important. And now I always remember that actual goes first because actual begins with A. A is the first letter of the alphabet, so actual minus predicted. Now, notice looking at the graph here that the residual, again, is the distance from the point to the line. So the line is what's predicted, the point is what's actual. That distance is your residual. So some residuals are positive because the distance between the point and the predicted line is positive, meaning it's above. So if I take the actual cost minus the predicted cost, since the actual cost is higher, I'm going to get a positive number. So all of these guys up here have positive residuals. And some residuals, this one's going to have a very small residual. I mean, look, it's almost exactly as predicted. Some points are going to have negative residuals. Again, these are all negative residuals as well. So a residual is simply the actual price minus the predicted price. Okay? So if you recall, I had that 84,000 mile car, and I predicted it to cost $24,573.40. Now let's say that car actually cost $24,000. The legit actual price was $24,000. So to get my residual, I would take the actual price, $24,000, minus the predicted price, $24,573.40, and I'd get a residual. The residual would be the actual $24,000 that it cost minus the predicted cost, and I would get a negative $573.40, which means that it was predicted to cost more than it actually was, right? A negative residual means the prediction was over the actual, or you could look at the other way around, and it actually cost less than predicted. So the cost of that truck was less than predicted. So a negative residual is your actual price is below the predicted price. So a couple comments about residuals. First off, notice that your line is trying to make all of those residuals as small as possible. It's trying to keep everybody happy. If it goes too close to some points and further away from others, that's not a very good line. So a good line is one line that has all of your residuals add up to 0. So if you were to add up residuals, you should get 0. Why? Because the positives and the negatives should cancel out. That is a good picture of the residuals. Now, next up is what we call a residual plot. Now, this is pretty easy, but I'm going to do my best to explain here. A residual plot is a plot of all the residual values. Okay, now go back to our picture here, right? Some residuals were positive, some residuals were negative. Some residuals were small, some residuals were large. So if I were to actually plot, actually I forgot I recopied it here. Here's the original scatter plot right here. Here's a residual plot. A residual plot shows the actual values of the residuals. Now notice right here 0, right? So I'm going to have a lot of positive residuals and a lot of negative residuals. That makes a lot of sense. That corresponds with here's the positive residuals, here's the negative residuals, right? And notice that it's scattered. The residual plot is completely scattered, and that's actually a good thing. This residual plot should show nothing because a good line is balancing all the points out. So some residuals are going to naturally be small. Let me point out a couple. Like this one right here is a small residual. Here's a small residual. Here's a small residual. Some residuals are going to be medium, like this one, and 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 this one. And some residuals are going to be large, like these guys. Again, the line has to keep everybody happy. So there's going to be this balance of positive and negative residuals and this balance of small residuals and large residuals. So if you were to graph the residuals, you should see scatter. You should see positive and negative. You should see some small residuals near 0, like this guy, this guy, this guy, and this guy. You should see some median residuals like here and here and here. And you should see some large residuals like these guys. So a residual plot shows nothing. It shows scattered. So this brings us to what is an appropriate linear model. How do I know a linear model is appropriate? Well, there are two things. You need to mention both to understand when a residual plot is, when a linear model is appropriate. First off, your original scatter plot. Your scatter plot of x versus y should be somewhat linear. And that's that word somewhat, which is a little bit vague, but it's just got to be, you don't see a major curve, basically. Your linear model is appropriate if your data is somewhat linear. That's pretty easy. It's vague on purpose. 2, the residual plot should show scatter. Remember, this is a good thing. A residual plot that shows scatter is a good thing. In class, we're going to talk about curved data and why curved data has a bad residual plot. Remember, a bad residual plot is one that shows a pattern. We want this is beautiful right here, what I have drawn here. We want a scatter plot that shows a linear pattern like this one does right here, and then we want a residual plot that shows nothing, because a residual plot that shows nothing shows that you have your points scattered around your line in a nice fashion. And if your points are scattered around your line appropriately, a picture of those residuals should show nothing. Okay, so hopefully that makes sense. In class, we're going to talk about how to make residual plots on our calculator. We already learned how to make scatter plots on our calculator. So we're going to teach you how to make a residual plot in your calculator. That way you could check and make sure that your residuals are, well, scattered. That's a good thing. In class, I'll explain a little bit more as to why that is really, really important. But hopefully you get a major point of it here in this video. All right, lastly, we want to talk about the very last thing for today's video is the official name. The official name for regression line is called a least squares regression line. Okay, this is extremely important. We called it LSRL for short, least squares regression line. Where does it get its name? Well, it comes from a very simple idea that we want our residuals to be as small as possible, right? A good line, a line that goes through your data, a line that's really, really good at making predictions is a line that has a lot of small residuals. But sometimes your residuals are bigger than they need to be. What are you going to do, right? You're trying to find the best line that goes through your data, and that's going to result in some small residuals and some larger ones. It just happens. Now, if we add up all the residuals, we talked earlier, you're going to get 0. Okay, that's a good thing. It tells us that we have a good mix of positive and negative residuals, but the number 0 isn't really used mathematically because, 0 doesn't, you can't really do a whole lot with 0. So what we do is we square the residuals, right? We square the residuals. We take each residual, y minus y hat, and we square it. And that's what this picture right here is showing. It's showing square residuals, right? So it's showing all the residuals squared, turns them into little squares, boxes, right? And we want the sum of those squared residuals to be as small as possible. And that's what this is right here. That little e is the symbol for the summation. We want the summation of all of the residuals to be as small as possible, the sum of the square residuals. That's where it gets the name the least squares regression line, because we want the sum of the square residuals to be as least or as small as possible, right? So if you think about it, this makes complete sense. Even if we have a scatter plot, let me just draw a quick scatter plot. Even if we have a scatter plot where they are all very, very tightly compact, I'm talking a correlation of like 0.98, very, very strong, right? Well, if I were to make a line through this data, right? In terms of these points, I still have some small residuals and I still have some large residuals. Now, it's all relative to your picture. Here, a large residual is not very large, but there are a lot of points that are really, really close to it and some that are a little bit further away. I still have positive residuals above. I still have negative residuals below. If I add them all together, I'm still going to get 0. And if I take the sum of the square residuals, I'm still going to get a number, because when you get square numbers, you're going to get a number. And it's that sum that I want to be as small as possible. Now, think about that green line. Now, think about this line, right? If I tried to use this as my line of best fit, or my regression line, that's just stupid. It doesn't even go through my data. All of my residuals are negative. Well, that's not a good thing, right? All of my residuals are large. That's not a good thing. The sum of those square residuals are going to be huge. They're all very far away from the pink line. Hence, when I square them, they're going to be really big, and I'm going to get a very large sum. That's not a good line. What's a good line? A good line is like this green one that creates positive and negative residuals, and it makes them as small as possible. That way, when you square them and add them, you still get a number that's as small as possible. And we say as possible, we're comparing it to other lines. So hopefully that was a quick, nice, simple video over linear regression. Please make sure the most important thing, if I had to emphasize what's the most important thing in this video, is being able to identify slope and y-intercept and interpret them in context. We're going to get a lot of practice of that in class, I promise.